Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 3450, Mission to Mars, Lecture 5, Early Spaceflight. With this lecture, we're going to take the course in a very different direction. The first third of the class, lectures 1 through 4, were about the basics of spaceflight, the things that we needed to know to understand how spaceflight happens, the laws of motion, the law of gravity, and all the concepts that we studied about orbiting bodies and orbits. In this part of the course, we're going to study how spaceflight actually was developed and how spaceflight is carried out. And we'll do it through a historical retrospective. We'll begin in this lecture with early spaceflight. We will move on to human spaceflight, early human spaceflight, the Apollo missions to the moon, the Space Shuttle, the International Space Station, and then modern launch vehicles. In the last third of the class, we'll talk about how a mission to Mars might actually happen based on the techniques of spaceflight that have been developed up to now, and we will talk about the new technologies that need to be developed to get us to Mars. So let's begin this second part of the class, which is the history of spaceflight. Now, there are thousands of people that have contributed to the development of spaceflight through human history. We could go all the way back to the Greeks if we wanted and find some Greek scientists who had ideas. But to keep it short and to limit the number of people, I thought I would start with Isaac Newton, who we've already seen when we talked about the law of gravity. Isaac Newton is probably the greatest of the physical scientists, and I think he's the natural starting point when we talk about spaceflight because of his development of the laws of motion and the law of gravity. You might remember the story of how Newton did this. In 1665 to 1667, he had just finished his bachelor's degree at Trinity College, Cambridge, when the Great Plague struck. The college was closed, Newton was forced to return home, and while he was home, he developed his laws of motion and the law of gravity. Now, he published them about 20 years later in 1687 in a treatise called The Mathematical Principles of Natural Philosophy, where he describes the laws of motion and he describes the law of gravity, and it's considered by many scientists to be the greatest work ever published in the physical sciences. Newton worked on many other areas. He studied optics. He built a reflecting telescope. He was interested in alchemy, amongst other things. He also developed calculus at the same time as Leibniz. But he clearly had a major influence on the development of spaceflight. The next person to have an impact on the development of spaceflight might come as a bit of a surprise, and that is Jules Verne, the French science fiction author. So Jules Verne wrote we wrote many books, but 4 that are famous among science fiction aficionados: A Journey to the Center of the Earth in 1864, From the Earth to the Moon in 1865, 20,000 Leagues Under the Sea in 1870, and Around the World in 80 Days in 1873. The second book I mentioned there, From the Earth to the Moon in 1865, describes what the first human flight to the moon might be like. Now, Jules Verne didn't picture it the way we did end up doing the Apollo missions. Rather than a rocket, he used a cannon. Rather than a spacecraft, it was essentially a giant artillery shell. It had a hatch on it, and the Voyagers climbed from a ladder into this giant artillery shell, and then they were launched by this cannon built in Florida, interestingly, where we ended up building Cape Canaveral, but launched from this giant cabin, launching that artillery shell into space and launching it to the moon. Although Jules Verne didn't get the details of how spaceflight would go correctly, what is remarkable is the influence that he had on those that did develop the techniques of modern spaceflight. And so I put him down as one of the great influencers because of his book, From the Earth to the Moon. If you're interested in spaceflight, I think From the Earth to the Moon is an essential read. Again, not because it tells you anything about spaceflight or how it's actually carried out, but because it was so remarkably influential on everyone that we will see coming up. The next person to talk about is Konstantin Tsiolkovsky. Tsiolkovsky lived from 1857 to 1935. He was born and lived in Russia. He was self-educated, taught himself mathematics and physics. Using physics and mathematics, he worked out the basic equations and the basic concepts behind rocket flight and rocket propulsion in 1896. In particular, he developed an equation that we will see later in the semester called the rocket equation, or sometimes called the Tsiolkovsky equation, that describes how much fuel you have to bring in order to launch a rocket and to get all that fuel moving. Tsiolkovsky designed rockets, he designed space colonies, he was truly a space visionary. Unfortunately, his early work, or most of his work, was not very influential, and that's because most of it was published in obscure Russian journals that were not available and not widely read among scientists and engineers in the West. The first and most influential of the U.S. rocket designers was Robert Goddard. In his honor, NASA has named the main NASA facility in Maryland the Goddard Spaceflight Center. It's located just north of Washington, D.C., near Greenbelt, Maryland. Robert Goddard was born in Worcester, Massachusetts. He was heavily influenced by Jules Verne's From the Earth to the Moon. That inspired him to take up rocketry, to work out independently from Tsiolkovsky the equations of rocketry and spaceflight, including independently deriving the rocket equation, but doing it much later than Tsiolkovsky had done it. Most importantly, Robert Goddard built and flew multiple stage rockets and liquid-fueled rockets. Here's an example of one of his liquid-fueled rockets. So the engine is actually up here at the top. This is the combustion chamber with the expansion nozzle down here. The fuel was gasoline and oxygen, and they were located in these tanks down here, and they were sent up through these lines where they were mixed in the combustion chamber. They were ignited, and they burned and propelled the rocket upwards. Goddard held over 200 patents, many of them related to rocketry and spaceflight. But unfortunately, Goddard was ridiculed in the 1920s. People in the 1920s didn't see the value in sending spacecraft into orbit around the Earth or sending humans into space. And as you saw in your first homework assignment, Robert Goddard was ridiculed in the early days, though he was very, very influential in the development of rocketry in the United States. The next person that I want to mention is Hermann Oberth. Hermann Oberth was another engineer and scientist that was inspired by Jules Verne's From the Earth to the Moon, which he read at age 11. Oberth was a German physicist and an engineer. He published influential works on spaceflight, on the basics of spaceflight, worked out many of the same equations that Tsiolkovsky and Goddard did, and he expanded on those and built on those. He also, like Goddard, built and launched rockets. Oberth is primarily known, though, as the mentor and teacher to Wernher von Braun. And so let's go on and talk about von Braun. Von Braun was a German rocket scientist and engineer. Was born in 1912, lived until 1977. He had heard about and was interested in the work of Robert Goddard. That inspired him to go to school to learn about aeronautics and astronautics, to learn about rocketry. He studied under Hermann Oberth, and Hermann Oberth took Wernher von Braun in as his mentor, as his mentee. Oberth was his mentor. Von Braun is considered to be the greatest rocket scientist of the 20th century. I should say the greatest rocket scientist in history. And this is largely because of his work in designing and developing, building and deploying the V2 rocket. It's worth spending a few minutes here to talk about the V2 rocket and the influence that it had on the future of spaceflight. The V2 rocket was developed by Germany as a vengeance weapon. The goal of this weapon was to terrorize civilian populations. The rocket could be launched from Germany or Western Europe. It would fly and it would land on cities in Europe. It was deployed against both Antwerp. It was deployed against London. It was deployed against a number of other cities, but Antwerp and London suffered by far the most hits from the V2 rocket. But the goal of this rocket was to rain terror down on the civilian populations. Altogether, during World War II, about 9,000 civilians were killed by V2 rockets. V-2 rockets flew supersonically, and because they were flying faster than the speed of sound, they would hit with no notice. You couldn't hear them coming. But also because of that, they were unstoppable. You couldn't shoot them down. They were too fast, and as I said, you had no indication that they were coming. They were launched from mobile platforms, so even if you could work from their trajectory back to where they were launched, the Germans were able to develop a number of launching areas so that they couldn't send bombers there to attack those launch areas. The V-2 is also infamous for the fact that it was built by slave labor during World War II in a concentration camp. About 12,000 laborers died in the production of the V-2 rockets. Now, what made Wernher von Braun probably the greatest rocket scientist in history was he was trained as a physicist and learned a lot of engineering under the tutelage of Hermann Oberth. And although he was a good physicist and a good engineer, he was actually brilliant at designing and running and operating engineering systems. That is, what Wernher von Braun's real strength is building engineering organizations that could have thousands of people working on designing individual parts of a rocket, constructing those parts, bringing the parts together, constructing the rocket. We would call that today integration, where you bring all the parts together, testing all of this, and then launching these rockets. He had a vision of how to do these giant engineering projects, and that is what he was truly brilliant at. That was his real genius. So how did the V-2 rocket work? It's worth, as I said, spending a few minutes talking about it because it is tremendously influential in the design of the earliest rockets in both the United States and in the Soviet Union. So the V-2 was a liquid-fueled rocket. It was fueled by a mixture of alcohol and water and liquid oxygen. The alcohol and water were the fuel. The oxygen was the oxidizer. So it was a liquid-fueled rocket. The alcohol and the liquid oxygen would flow through these tubes to a turbine pump assembly. So this is the way that many modern rocket engines, liquid-fueled rocket engines, are powered today, are by turbopumps. The alcohol and the liquid oxygen were pumped into the combustion chamber. The combustion chamber is where the alcohol and the oxygen were brought together, but they had to be ignited, so there was an igniter in there as well. It lit the alcohol on fire. It consumed the oxygen, and the alcohol was oxidized by the oxygen, got up to tremendously high temperatures, passed through this narrow throat in the combustion chamber. As it passed through that small throat, it picked up speed, and then it went out the exhaust nozzle at the bottom of the rocket. This was very much the very first modern liquid-fueled rocket. The rocket was controlled by a series of control vanes that were located on the tips of the fins right here, and then there were also a number of control vanes that were in the exhaust. These were made of graphite, so that even though they were in the extraordinarily hot exhaust coming out of the engine, the graphite would allow them to survive, and these vanes could be tilted back and forth, and they could be used to steer the exhaust of the engine, in addition to the aerodynamic steering that came from the ailerons that were out there on the end of the control fins out there. The V-2 rocket was the first long-range guided ballistic missile. It was guided because up here at the top of the rocket was a control compartment, and the controls allowed this rocket to be guided to a target, and it was a long-range ballistic missile. In fact, in one launch in Germany in 1944, the V-2 rocket was the first human-made object to make it above the Kármán line, which is 100 kilometers or 62 miles above the surface, that artificial line where we define space as beginning. The way the V-2 rocket was deployed is it was launched vertically. Shortly after launch, when it was about 10 kilometers high, it rolled over onto its side. It continued firing its engine, got up to a peak acceleration of about 5 Gs when the engine shut off, and then it continued on this trajectory ballistically, which meant the engine was no longer firing, but its momentum carried it all the way up to about 60 kilometers, so about a little less than 40 miles in altitude, and then it would come back down, steering itself, guiding itself all the way down until it would crash at its designated target. Because of the weapon that it carried, up in the top it carried a warhead full of high explosives. Because of the warhead and because of the sheer kinetic energy of this large, massive object coming down supersonically, a V-2 rocket could do a tremendous amount of damage. As I said, 9,000 civilians were killed by the V-2 rocket. This is an example of damage that was done by a single, all the damage that you see here was done by a single V-2 rocket striking in London. So as I said, von Braun's brilliance was in engineering management, building these large engineering systems. At the end of World War II, von Braun and about 126 of his colleagues or so, the principal designers of the V-2 rocket, faced a choice of surrendering to the Soviet Union or surrendering to the United States. They were afraid that if they surrendered to the Soviet Union, they might be shot, and so they decided instead to surrender to the United States. As part of that surrender, they gave over about 300 carloads of V-2 parts and rockets, and they were captured and shipped to the United States. Von Braun and these 126 principal designers of the V-2 rocket, and in fact, about 1,600 other scientists and engineers associated with other projects in Germany were brought to the United States as part of an operation called Operation Paperclip. Now, the United States used von Braun and his principal designers. They worked with U.S. rocket designers and U.S. aerospace engineers to construct about 80 V-2 rockets from the parts that were captured. And these rockets were test launched in the United States, and they were used to develop the very first rockets that the United States developed. At the same time, the Soviet Union did the same thing. The Soviet Union also captured a number of V-2 rockets. They captured a number of personnel that were responsible for designing and building the V-2 rockets. They also captured the manufacturing facilities where the V-2 rocket had been built. They reestablished V-2 production in Germany, and they eventually moved it to the Soviet Union. So the early rockets in both the United States and the Soviet Union were based on the V-2 rocket, which was developed by von Braun. Now, von Braun was also influential because he sold the idea of spaceflight to the U.S. government and to the U.S. public. He wrote articles for Collier's magazine. He produced specials for Disney. He was key to launching the first American satellite. He was key in developing some early American rockets, primarily the first stage of the monstrously huge Saturn V rocket that was used to send astronauts to the moon. So you'll see a Saturn V launching there on the left-hand side, and von Braun's group was largely responsible for building the first stage of that Saturn V rocket. Here's von Braun posing in front of the bottom end of the Saturn V. You can see just how monstrously huge that rocket was with the 5 giant F1 engines that powered the first stage there. It's important when talking about von Braun, though, to also talk about von Braun's history. He's often idolized as being the greatest rocket scientist of all time. But we also have to remember that he's a very complicated person with a very complicated history. Von Braun was a member of the Nazi Party. He was also a member of the SS. He oversaw not only the design of the V-2 rocket, but the construction of the V-2 rocket. And this was done in a concentration with labor from a concentration camp. And about 12,000 people died in this concentration camp producing the V-2 rockets for Germany during World War II. And during his life, von Braun never reckoned with this past history. He often passed it off, said that the concentration camp was far from where he was. He had no power to stop it. But it's important to realize that von Braun was in charge of this. He knew that slave labor was being used in the production of the V-2. He and none of the scientists from Operation Paperclip were ever brought up on war crimes charges for what they did, because their service to the United States was deemed so valuable by the U.S. government after the war that they didn't want to see these individuals prosecuted. But it is important to keep in mind what von Braun knew during the war and then largely denied or passed off after the war, and frankly never took personal responsibility for what he was responsible for during the war. Another person that we need to talk about, and it'll be the last of the individuals we talk about, is Sergei Korolev. Sergei Korolev is the chief rocket designer for the Soviet Union. He lived from 1907 to 1966. He was known as the chief designer as part of the Soviet rocket program. Initially, he oversaw the launching of the V-2 rockets that the Soviet Union had captured from Germany, and then eventually led the design bureaus that designed the Soviet equivalents, the first Soviet rockets. So, for example, he was responsible for the development of the Semyorka R-7 rocket, which was used to launch Sputnik. He was responsible for the design and the launch of Sputnik 1, of Sputnik 2. He was responsible for the design of Vostok 1, which launched the first human into space. He was responsible for the design of the Soyuz spacecraft. He was even responsible for the design of the massive Soviet N-1 rocket, which was supposed to take Soviet cosmonauts to the moon, but was never finished. I shouldn't say it was never finished. It launched a few times, but was never successful in getting Soviet cosmonauts to the moon. Sergei Korolev, I think, is also one of the greatest rocket designers of the 20th century. And if you just look at his list of accomplishments here, the first satellite, the first animal in space, the first human in space, the Soyuz rocket and spacecraft, which are still used to this day, I think you could make a case that Sergei Korolev is probably the greatest rocket designer of the 20th century. And so that is our brief history of some of the really influential individuals. As I said, there are thousands of others that we could have covered, but let's move on to talking about the history of spaceflight. As we talk about the history of spaceflight, I want you to think about the design of the spacecraft that are being launched. We're not going to have a lot of time to go into this semester, but there are just some things that I want you to keep in mind, and the lecture exercises that come with this lecture will ask you to consider some of these questions about the spacecraft I'm talking about. So a spacecraft needs power. There's lots of ways a spacecraft can get power. They can be battery powered. Of course, a disadvantage to batteries is eventually they run down. They can be solar powered, where you get power using solar arrays from the sun. You can use something called fuel cells, where you mix a fuel and an oxidizer together, and the heat from that reaction can generate electricity. That usually you put a bimetallic strip, two metals that are dissimilar to one another, and by heating it up, heating one side of it up and keeping the other side cold, you can generate an electric current across it. So a fuel cell uses a chemical reaction to generate electricity. And then, of course, there's nuclear power. In addition to power on a spacecraft, we have to talk about attitude control. We want some way to control how our spacecraft is moving through space. So some early spacecraft had no attitude control. They were literally launched and they could just tumble end over end. You can use gravity to stabilize a spacecraft if it has a heavy end to it. A spacecraft naturally over time will orient itself with a heavy end pointing down towards the Earth. You can spin a satellite, and spinning a satellite keeps it stable. You'll remember the pictures that we showed back in the basics of spaceflight about a spinning gyroscope, a spinning wheel, how it maintains its orientation, and then if you push on it, it wobbles or precesses. You can use a spin of a satellite to keep it stable. You can change the attitude of a spacecraft by using magnetic torquer bars. So you can use big bars that have loops of wire on them to create a magnetic field. And that magnetic field can push and pull against the Earth's magnetic field to twist the spacecraft. You can have spacecraft that are three-axis stabilized. That is, that they're neither rolling or pitching or yawing back and forth, and they can do this using gyroscopes or big giant spinning wheels called reaction wheels, or sometimes called momentum wheels, or control moment gyroscopes. You can also orient a spacecraft, and many today are still oriented using sun sensors, a sensor that finds the sun in the sky, or star sensors that actually can identify individual stars in the sky, or a horizon sensor that might look for the horizon of the Earth. And of course, some spacecraft, but not all, have a propulsion system. I alluded to this fact that you want to control how your spacecraft is oriented, and for any spacecraft, we define 3 axes of rotation, and we call them roll, pitch, and yaw. Roll is motion about the axis in which you're traveling. So if you think about an airplane for a second, rolling is that sort of clockwise or counterclockwise motion as the airplane moves forward. Yaw would be the side-to-side motion, and pitch would be up and down. And for spacecraft, we can define exactly the same thing. Whether it's a Mercury capsule, we can define the roll, the pitch, and the yaw. We can do the same thing with robotic spacecraft today. So we need some way to maintain our orientation in space if it needs to be maintained. If it doesn't, we could just let our satellite tumble. There are also things that we have to consider, like thermal control of a spacecraft. How do we keep the inside at a manageable temperature? Many spacecraft today, you'll see, are covered in these gold blankets, these insulation blankets, and they serve 2 purposes. On the day side of the orbit, when the sunlight is beating down on them, they keep most of the heat of the sun out of the spacecraft. And then on the very cold night side of the orbit, those same thermal blankets keep the heat in the spacecraft trapped inside so it doesn't get too cold. There are active ways to control thermal. You can put little open louvers, doors that open and close on the spacecraft to let heat radiate out, or close them down to keep the heat from radiating out. You can use, as they do on the International Space Station, tubes filled with ammonia and water to transport heat from inside the spacecraft, where it can be very hot, to giant radiators that radiate that heat out into space. A spacecraft needs communications. We want it to talk to us. That's typically done using radio waves. There'll be a radio transmitter and an antenna on board, and it'll be sending radio waves down to us. If we want to control the satellite after it's launched, it needs some kind of command and data handling system. A command system allows it to receive commands from the ground and execute those commands. Today, we would think of that as the computer on board. Many early satellites didn't have computers on board. In fact, they had no way to do command and data handling. Once we launched the satellite, it did its thing without being controlled by us. Data handling is basically, how do you handle the information on board the spacecraft and get it down to the ground through the communication system. And then ultimately, there's the payload on board. Why did we launch this thing to begin with in the first place? So typically when we think of a payload, we might think of scientific instruments on board. I raise all these issues because as we go through these early projects, I want you to think about the decisions that the scientists and the engineers were making in the design of the spacecraft. How did they power them? Was the spacecraft, did it have attitude control? How did they control its attitude? How did they control the temperature of the spacecraft? How did it communicate with us? Were we able to command and control it? What kind of payloads did it have? I want you to think about these, and then as you do the lecture exercise, you'll answer some questions based on a couple of the satellites, a couple of the programs that you're about to see. You'll answer questions about that. So let's talk about the idea of launching a satellite into space. So in 1952, the International Council of Scientific Unions declared that the year 1957 would be known as the International Geophysical Year. And in 1954, the Council adopted a resolution that called for the launch of an artificial, human-made satellite to orbit the Earth during the International Geophysical Year. So in July of 1955, the United States announced plans to launch an Earth-orbiting satellite as part of the International Geophysical Year. This would be a human-made satellite to orbit the Earth. Now, the United States at the time had 2 potential programs. There was the Naval Research Lab, and they had a program called the Vanguard rocket and the Vanguard satellite, and they were proposing Vanguard as the U.S. launch vehicle. As we'll see a little bit later, the U.S. Army had a separate system. They were using the Jupiter missile, the Jupiter rocket, with the Explorer spacecraft. Von Braun was involved in the Explorer side. He was with the other one. But in 1955, the Naval Research Laboratory's Vanguard proposal was chosen as the rocket and the satellite that the United States would launch during the International Geophysical Year. Now, the Vanguard satellite was just a little tiny thing. It was about 3.5 pounds. It was about the size of a grapefruit, had a couple antennas sticking off of it, and you'll see more about that here in a minute. But the United States publicly announced plans to launch an Earth-orbiting satellite. So in 1957, the United States was getting ready for the launch of Vanguard 1, getting ready to launch this first orbiting artificial satellite, probably going to happen at the end of 1957, when the United States was shocked in October of 1957 by the launch of Sputnik 1. So Sputnik 1 was the first satellite in orbit, and it was built and launched by the Soviet Union. This satellite was huge compared to what the United States was considering building. Remember, the United States was building, I should say, and was considering launching something that was about the size of a grapefruit. The Soviet satellite, Sputnik 1, weighed 84 kilograms, had a mass of about 184 pounds. So it was much, much bigger than what the U.S. was planning to launch. And it was launched on October the 4th, 1957, on an R-7 Semyorka intercontinental ballistic missile. So the Soviet Union had developed the R-7 Semyorka to deliver nuclear weapons, to essentially bomb the United States with nuclear weapons. The nuclear weapons in the 1950s were massive compared to nuclear weapons today. They were big, they were heavy, they required a very large rocket to launch them. So the Soviets developed the R-7 Semyorka to deliver these nuclear weapons. And Sergei Korolev got the idea that they could modify the control system, modify this intercontinental ballistic missile, and instead of going up and down on the United States, they could modify it to put a satellite in orbit around the Earth. So they then developed the satellite, Sputnik 1, put it on an R-7, and launched October the 4th, 1957. There are very few dates that I want you to memorize. This is one of them. So in fact, I'm going to ask you to go out to the lecture exercise and answer the very first question out there, which is, what was the date that Sputnik 1 was launched? October the 4th, 1957, right? It's a date you need to remember because that's the beginning of the space age. That's when we launched the first artificial satellite. It was launched into a 96-minute orbit that was 134 by 583 miles in size. So very elliptical orbit, took 96 minutes to orbit the Earth. So that's what Sputnik looked like. There was a transmitter on board that was battery operated, didn't have solar cells, had no way to recharge the battery, so it transmitted for 22 days and then the battery ran out. It had a 1-watt transmitter, and it transmitted through these antennas that you can see coming off the side of the spacecraft here. So these big, long whip antennas that you see right here are dipole antennas, and it just broadcast a radio signal, transmitted on 2 different frequencies, 20 megahertz and 40 megahertz. And what Sputnik was famous for was just sending out the famous Sputnik beep. Now, those beeps actually had a meaning, and those beeps would change in frequency. They would change how often they were occurring based on the temperature and pressure inside the spacecraft. So the Soviet Union could monitor the rate at which the beeps were being sent out, and it would give them an indication of what the temperature and the pressure inside the spacecraft were doing. Now, Sputnik re-entered the Earth's atmosphere on January the 4th, 1958, so it was not a long-lived satellite. You can see it was launched in October, re-entered in January, so it was just a couple months. This is what the interior of Sputnik 1 looked like. Had no attitude control system, so Sputnik was put up there and it was allowed to tumble end over end. It didn't have any cameras, it couldn't point and take pictures of anything, so there was no need to keep it oriented. In fact, the only thing that it really carried was the transmitter. And the whole goal of that transmitter was so that people on the Earth could hear the satellite. If you had a radio receiver, you could pick up the beeping as the satellite passed overhead. And in the case of the Soviets who had built the system, they could monitor the rate at which the beeps were coming down and determine the pressure and the temperature inside of Sputnik 1. And of course, as we saw in the very first lecture, this was devastating to the prestige of the United States. The Soviet Union had a secret program to launch the first satellite, and they beat the United States to launching the first satellite. The U.S. reputation took an even bigger blow when the Soviet Union launched a second satellite into orbit, and that was Sputnik 2. Sputnik 2 was designed to carry the first animal into space, and that animal would be a dog. Now, Sputnik 2 was rushed into development. It was rushed to coincide with the eve of the 40th anniversary of the Russian Revolution. It was launched on November the 3rd, 1957, so one day less than a month after Sputnik 1. And it was put into a very elliptical 132 by 1,000 mile orbit with a period of 104 minutes. Now, Sputnik 2 was also launched on an R-7 Semyorka rocket. This time, the spacecraft on top remained attached to the upper stage, and the reason that it remained attached to the upper stage was that the communications system for the satellite was not ready at the time of launch. So they decided that by leaving it attached to the upper stage, they could use the communications system that was built into the upper stage to send signals back to Earth. So Sputnik 2 remained attached to the upper stage in order to use the telemetry system, the communications system on that upper stage. That resulted in rumors that the satellite did not properly separate from the upper stage, but that's not true. It was intended to remain attached because they had rushed it, and the satellite itself didn't have a working telemetry communications system. The passenger on board was Laika, a female terrier dog. She was a stray who was found on the streets of Moscow, was adopted, and was trained and launched into space. Now, the goal was to keep Laika alive for 10 days inside the spacecraft. There were no plans to recover Laika. There were plans to put her to sleep at the end of the 10 days, but the goal was to try and keep her alive in the spacecraft for 10 days, and then, as I said, put her to sleep once the 10 days were over. Unfortunately, the thermal design of the spacecraft failed, in large part because it was still attached to that third stage down below, and that didn't let the spacecraft bleed all of its heat off into space. Because of this mistake in the thermal design, within a few hours of launch, the interior of the capsule, where Laika was rose to about 104 degrees. Now, being that hot, Laika died both from heat and from stress, and so she died within a few hours of launch. She did not survive for even a day in orbit around the Earth. But Laika is, of course, famous for being the first animal launched into space. Sputnik 2 re-entered in April of 1958 after 162 days in orbit. So the Soviet Union launches 2 satellites into space. The United States hasn't launched any. So President Eisenhower was under tremendous pressure to get the United States to launch something. And so, as I mentioned, there were these 2 competing projects, the U.S. Navy Vanguard project and the U.S. Army Jupiter rocket with the Jet Propulsion Labs Explorer 1. The Vanguard project had a very widely publicized launch attempt on December the 6th, 1957. And you'll remember from the first lecture what happened in that launch attempt. The rocket lifted off from the pad. The first stage quickly failed. The rocket fell back down to the pad. It exploded in a tremendous fireball. The satellite itself, the little Vanguard TV3 satellite, was actually blown clear of the explosion. And here it is. You can actually see it at the Smithsonian. If you go to the Smithsonian today, you can see the Vanguard TV3 satellite that was destroyed in this first explosion. And you might remember some of the headlines that I mentioned in that first lecture. It was called Flopnik, Excusenik. There were all kinds of jokes and names made about the fact that the first U.S. attempt to launch a rocket, a very public attempt, was such a tremendous failure. At this point, focus moved to the U.S. Army's Jupiter rocket and the Jet Propulsion Labs Explorer 1 satellite. So let's take a look at this quick video clip.
The morning of November 8, 1957, at Huntsville, Alabama. A sudden meeting has been called by General John B. Medeiros, Commanding General of the Army Ballistic Missile Agency.
I have a very important announcement for you. We've been assigned the mission of launching a scientific Earth satellite. And we will use the Jupiter C configuration as a carrier that we developed along with the Jet Propulsion Laboratory. I promised the Secretary of the Army that we would be ready in 90 days or less. Let's go, Werner.
meanwhile, far across the country at the Jet Propulsion Laboratory, a sprawling 80-acre research and development complex in Pasadena, California, scientists and engineers were racing toward the same deadline: 90 days to put a satellite into orbit. Their job, furnish the high-speed upper stages to take over after the first stage powered the satellite to the prescribed distance from the Earth. The beams of powerful searchlights light up the missile. The drama approaches the final act, the Army's first attempt to fire a man-made moon into orbit. Late evening, Friday, January 31st, 1958, in a blockhouse at Canaveral. The countdown to Explorer 1.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. By command, by command. Think command.
The missile is in flight, but it will take another hour and a half to know whether the satellite is in orbit. About midnight, General Medeiros finally called his assistant, Colonel Leonard Orman.
Hello, Len. You can send this off to the secretary, that our satellite is definitely on orbit.
20 minutes later, Dr. Porter opened the question and answer session by introducing three of the key men in the success story of Explorer 1.
The question is, has any form of life been placed in the satellite? I think I could answer that one almost myself. Not intentionally.
Maybe we have a Florida cockroach inside, we don't know.
Just one more came the inevitable plea from the photographers. And exhausted as they were, the trio obliged with what was to be the page one spread in newspapers all over the world. The United States was in the space business along with the Russians, and Explorer 1 was the beginning.
So that was the launch, the U.S. launch of Explorer 1. The Explorer 1 satellite, as you saw there, was a long, thin, cylindrical satellite. It was spin stabilized. If you go back and watch the video of the launch, you'll notice that at the moment of launch, Explorer 1 is sitting on top of the rocket and it's spinning around very, very quickly, because when it was released from the rocket, they used that spin to stabilize it. For communications, it used a radio. These are the antennas right here, these little four wires that are sticking out are the antennas that it used. This rocket stage here was the upper stage that was used to put it into orbit. In terms of power, it was powered by batteries. There were no solar cells on it, and there was no way to like Sputnik 1, there was no way to command it. They could get data down from it, but they weren't commanding it to do anything. So, and there's the famous photograph of William Pickering, who was the director of the Jet Propulsion Lab, Van Allen of the Van Allen radiation belts, who designed the scientific instruments that were on board Explorer 1. Explorer 1 had on it a transmitter. There was a Geiger counter that would tell them the radiation in space, 5 temperature sensors, and 2 micrometeorite detectors. So that's what was on board. And then Werner von Braun over here on the right-hand side, who was largely responsible for the development of the Jupiter C missile. Well, now that both the Soviet Union and the United States had launched spacecraft, the space race began. Now, it's important to realize that in these early days of the space race, about half of all launch attempts were a failure. So we have Sputnik 1 being a success, Sputnik 2 being a success, Vanguard being a failure, Explorer 1 succeeding, Vanguard failing again, Explorer 2 failing, Vanguard 1C finally succeeding, Explorer 3 succeeding, Sputnik 3 failing, Vanguard failing, Sputnik succeeding, Vanguard failing again, Explorer succeeding. So it seemed about half the time. There were various errors. You can look there at the descriptions if you want to see as to why they failed. But this was a tough time as we were learning how to build and launch satellites. But we learned quickly. In that first year, 1957, there were 2 successful launches, Sputnik 1 and Sputnik 2. By the early 1960s, we were launching 50 satellites a year, and by 1964, we were launching well over 100 satellites a year. These are the space launches by country. The year is running across the bottom right here. We've got the number of launches right here. The United States launches are shown in blue. The Soviet Union, Russian launches are shown in red, and then the yellow is the European Union, and then there are launches by India, Japan, others shown on there as well. But what we're interested in is this early space age right now, when you can see that both nations, the United States and the Soviet Union, very quickly ramped up the number of launches, so that by the early 1960s, they're each launching close to 100 satellites per year into orbit. So I'm going to talk about some more famous satellites. So the first Vanguard satellite to make it into orbit was March 17th, 1958. It's called Vanguard 1. It was put in an orbit that was 406 by 2,466 miles. And what's special about Vanguard 1, two things that are special about it. First of all, it was the first satellite to use solar cells. So it had a small battery on board, but that battery was charged using the solar cells. And it happens to still be in orbit today. So it's the oldest piece of space debris that's left up there. It's no longer working, but both the satellite and its booster are still in orbit, the oldest things that still exist up there. It's expected to re-enter the atmosphere around the year 2240. I've already mentioned Luna 1, which was a Soviet mission, the E1 number 4 lunar probe launched on January the 2nd, 1959. Also launched on a rocket that was developed. It was based on the R-7 Semyorka ballistic missile. It was called the 8K-72 rocket. And you'll remember that this one was a probe that was designed to go to the moon, but an error in ground equipment sent it moving a little bit too quickly, so it was moving too fast and it missed the moon. About 34 hours after launch, it flew about 6,400 kilometers in front of the moon, but it had reached escape velocity, and so it was the first satellite ever to escape from the Earth. And so that's Luna 1 back in 1959, January 2nd of 1959. We send our first spacecraft with escape velocity to escape from the Earth. In the Luna series, another famous spacecraft is Luna 3. It was the first spacecraft to get around and photograph the far side of the moon. So if you've taken introductory astronomy, you've learned that the moon always keeps the same face towards the Earth. The side facing the Earth is called the near side of the moon. The side facing away from the Earth, which we never get to see, is called the far side or the dark side of the moon. And that far side is never visible from Earth. Luna 3 was the first spacecraft to get around to the far side of the moon. It was launched on October the 4th, 1959. It was also the first successful 3-axis stabilized spacecraft. Up until this point, the spacecraft either tumbled or they were spin-stabilized spacecraft like Explorer 1, but this was the first spacecraft that could hold itself orientation, hold itself still. That is, it could control its roll, its pitch, and its yaw. It could control all three. And it needed to do that because it was using a camera to photograph the far side of the moon. So how did they do this? Here's the Luna 3 spacecraft. And by the way, just so you've seen it, there's the first photograph that Luna 3 took of the far side of the moon. By modern standards, an absolutely terrible photograph, but it was, of course, the first ever photograph of the far side of the moon. You can see some dark splotches in the photograph. Those are maria or seas on the far side of the moon. Because Luna 3 took the first photographs of the far side of the moon, many of the most prominent features on the far side of the moon have Russian names because the Russians, the Soviets, were the first ones to photograph them and got to name them. The spacecraft used solar cells to power itself. It was 3-axis stabilized, and it used a sun sensor and a photocell to detect the moon. So the sun sensor determined where the sun was, the photocell determined where the moon was, and it was able to use those 2 points to hold itself still while it took the photograph. During most of the mission, it was just spinning. It was spin stabilized, but could steady itself to take photographs while it was taking photographs. They didn't have digital cameras in those days, and so the moon was actually photographed with a film camera. And the spacecraft contained an automatic film processing unit. That is, the film moved through the camera, the film was taken out of the camera, was moved to a batch of chemicals that were used to develop the film, and then the film was moved to a scanner that actually scanned the photograph in and sent those photographs back to Earth. Took a total of 29 images over 40 minutes. 17 of those images were transmitted back to Earth and 6 were eventually published. So that's a little bit about the Luna 3 spacecraft. You can see that it had a radio, so these are the ribbon antennas right here. So these were used for communicating with the Earth. I already talked about the fact that it had sun sensors for stabilizing itself, and it used solar cells for powering itself, including a battery inside. So that was the Luna 3 mission. The first commercial satellite, up until this time, all satellites were owned and operated by governments. The first commercial, privately owned satellite was built by AT&T Bell Labs. It was called Telstar, and it was launched on July the 10th, 1962. And it was the first transmission of a telephone and television signals via satellite. So the first transatlantic television broadcast, let me bring up, there's a video here that I want to show you.
From a ground station nestled in the mountains at Andover, Maine, a signal is sent to a speeding satellite, an historic feat that could reshape man's future. That satellite, of course, is the Telstar. 170 pounds of complex electronic equipment that receives signals beamed from Earth, magnifies them 10 billion times, and rebroadcasts them back to Earth. Pictures, telephone calls, telegraph messages, and computer data all can be handled by the orbiting device. The Telstar receives its power from batteries that are recharged by the sapphire-coated solar cells, which in turn are activated by rays from the sun as it hurtles through space at a low point of 600 miles to a high of 3,500 miles. The Telstar is sent aloft from Cape Canaveral atop a Thor Delta rocket in a joint industry government effort. The Space Administration team handles the launching for AT&T, and it's a $50 million phone call for the telephone company. Future plans call for the orbiting of 20 to 25 satellites like the Telstar. Thus, when one passes out of range of ground stations, another will be coming into position. Presently, along with the ground station in Maine, there is a receiver and transmitter in Great Britain at Cornwall, and in France on the coast of Brittany. Even as Telstar is launched, the French rush to complete their installation to receive a signal that night. Now the rocket climbs far into the atmosphere, and the Telstar is about to separate and orbit the Earth each 2.5 hours. Starting with the 6th orbit and through the 9th, the Telstar is in range of both the U.S. and European stations, and pictures are received clearly in France, with somewhat lesser success in Britain on this first test. The signals are beamed from this 18-story dome that houses the super-sensitive horn weighing nearly 400 tons, an antenna so delicately tuned that it picks up a mere whisper of a signal from the satellite and amplifies it again billions of times for rebroadcast over cables or the air. Now comes the historic moment, a moment compared in significance with the first message sent over the telegraph. This is the first picture transmitted to outer space and received back again on Earth. Scenes of the dome at Andover are flashed across the sea, and man marks another milestone in this age of scientific miracles. So proudly it waves. What does the future hold? Well, scientists visualize a belt of Telstars encircling the globe in such a manner that transmission will be continuous around the world. Both sides of the Earth can be in immediate photographic contact, communication that could bring better understanding among men.
I mean, it's hard to remember today when I can get on the internet and can download videos and photographs and anything from around the world. what it must have been like in 1962 when you couldn't do that. In 1962, if there was a live broadcast in the United States, in order to see that in Europe, that film had to be loaded on an airplane, had to be flown across the Atlantic Ocean. There was no way to transmit those images overseas. And so now, for the first time, live broadcast could be sent around the world. In fact, the very first live broadcast that was sent to Europe was a baseball game between the Philadelphia Phillies and the Chicago Cubs at Wrigley Field in Chicago. They also broadcast some remarks by President John F. Kennedy. Now, what was interesting about the Telstar satellites is you saw they were not in geosynchronous or geostationary orbit. They were in a much lower orbit, orbiting the Earth every couple of hours. And so as one satellite would continue in its orbit and would move out of range, you would need another one to come into view. The very first geosynchronous and geostationary satellites were SYNCOM-2 and SYNCOM-3. SYNCOM-2 was launched on July 26, 1963, and SYNCOM-3 was launched in August of 1964. And they were both put into, SYNCOM-2 was geosynchronous and SYNCOM-3 in geostationary orbit. These were spin-stabilized satellites. So these would spin, obviously powered again by solar arrays that you can see right here. These early ones were very simple satellites. They had an antenna sticking, the top thing right here is an antenna sticking off the top. And these satellites were designed to test the idea that you could put a satellite in geosynchronous and geostationary orbit and have it stay above one point on the equator. So these were the predecessors to our modern day communications satellites. Now, of course, there were military developments, and the military immediately saw the use of being able to use space. So amongst many other things, the United States developed spy satellites. One of the early, very capable programs was called the Corona program, which was a upper stage of a rocket that was modified to have a large camera on board. So when that upper stage was put into orbit, the camera could photograph the surface of the Earth. It could be programmed from the ground. So that is one where it was not only launched and would photograph the Earth, but the controllers on the ground could tell it where they wanted the photographs taken. Now, interestingly, this was still the era before we had digital photographs. So once the camera took photographs, how did they get back to Earth? Well, the rocket carried with it a couple of re-entry capsules. What would happen is after it had used all the film, it would put the film in one of these re-entry capsules. The spacecraft would spin itself. When it spun itself, it would let go of this reentry capsule, which itself was spinning very, very quickly. And that reentry capsule would enter down. It would use a heat shield to come through the atmosphere and come back down to the surface. And in fact, the Corona satellites are the first satellites to re-enter the Earth's atmosphere, survive, I should say, re-entry into the Earth's atmosphere. Of course, Sputnik 1 re-entered the atmosphere but burned up. So what the inside of the Corona looked like, where there were cassettes that had all the film. These were the take-up cassettes. This was where the film was supplied from. These were the panoramic, rotating cameras. And then the film would go through, and then it would be put into these take-up cassettes. And those take-up cassettes would be put in the capsule and brought back to Earth, where they would be developed. And then those on the Earth could look at these photographs. The Corona mission provided images of the surface of the Earth that were better than anything that could be obtained otherwise. And most importantly, at this time, the Soviet Union was developing the ability to shoot down spy planes. So this allowed the United States to spy on the Soviet Union with no chance of the aircraft being shot down. Famously across the United States, there were calibration targets that were built, these concrete targets. If you go out, especially to the desert southwest of the United States, occasionally you will encounter these large, they look like crosses made out of concrete, and these were actually calibration targets. They would have the Corona satellites photograph these calibration targets to help calibrate them. The container, the reentry capsule itself, had a heat shield on the bottom, and then the film was stored inside of it. It would parachute down through the atmosphere, and then as it was parachuting down, the parachute was caught by an airplane. A flying airplane would come by and snag the parachute out of the air and grab it that way. So that was first capsule to first spacecraft to have capsules that could re-enter the atmosphere. A couple of other interesting firsts. Mariner 4 was the first successful flyby of Mars, launched on November the 28th, 1964 on an Atlas Agena rocket, flew by Mars on July the 14th, 1965, returned 22 images of Mars. Did not go into orbit around Mars, it just flew by Mars. It was a solar-powered spacecraft, had a camera on board, had a larger, because it was going all the way to Mars, now it needed a much larger antenna to be able to send those signals back to Earth. And as it flew by Mars, it took photographs revealing that Mars was not covered in vegetation. It did not have animals. It did not have large cities. It was, in fact, like the moon, a heavily cratered body, very cold and very dry. Luna 9 was the first spacecraft to successfully land on the moon. It was a Soviet spacecraft, landed on the moon on February the 3rd, 1966. So it was the first robot to land on another body anywhere in the solar system. The United States would follow this with a series of surveyor spacecraft that would land on the moon to prepare the way for the Apollo spacecraft. There were concerns that the lunar dust could be deep enough that it would swallow astronauts and swallow spacecraft whole. And so the United States developed a series of surveyors that were sent before the Apollo missions to land on the surface, photograph the surface, and test the surface of the moon. The Apollo 12 mission, as you'll remember reading in A Man on the Moon, the Apollo 12 mission landed very close to the Surveyor 3 spacecraft. And so that's how we have this image of Surveyor 3 sitting on the surface of the moon. Mariner 9 was the first spacecraft to orbit another planet, and it orbited the planet Mars. So it was launched on May the 30th, 1971, and it was the first time that humans were able to send a spacecraft to another planet, slow it down, and get it into orbit. Now, Mariner 9 arrived during a giant dust storm on Mars. It arrived at the same time as two Russian spacecraft called Mars 2 and Mars 3. The difference between Mariner 9 and Mars 2 and Mars 3 is that the Soviet spacecraft were designed to carry out their missions with essentially no input from the ground. They arrived at Mars, and unfortunately, when they arrived, a giant dust storm was raging on the surface of Mars. So they expended all their film and they took all their photographs when there was nothing to see because the dust storm completely obscured the surface. Fortunately, the United States, with Mariner 9, was able to control the spacecraft, and they were able to hold off taking many images until the dust storm settled out. And Mariner 9 is famous, of course, for discovering the giant volcanoes, Olympus Mons, and the other volcanoes on the Tharsis Bulge, and it discovered a giant valley on Mars, a valley so big that it would stretch all the way from San Francisco to New York City if it were located on the Earth. And in honor of Mariner 9, it's called Vallis Marineris. Mars 2 and 3, those spacecraft that orbited around Mars, also contained the first landers to attempt to land on Mars. And Mars 2 and 3, Mars 2 ended up crashing to the surface, and Mars 3 ended up soft landing and surviving for about 110 seconds before it stopped transmitting. And so those were Mars 2 and 3. Of course, NASA built the NASA Mars Viking launched in 1975, arrived at Mars in 1976, and the Viking consisted of two spacecraft. Each one was an orbiter, but also had a lander on board. And so these are images that were taken by the Viking spacecraft in orbit around Mars. And the two landers that landed on the surface, these landers were nuclear powered down on the surface. They did not have solar cells. They were powered by small nuclear reactors. Viking 1 and Viking 2 both successfully landed on the surface of Mars, and they returned the first clear images from the surface of Mars. So these were the first landings where we got clear images back, and that is the very first ever image that was returned from the surface of Mars. And then here's a panorama taken by Viking 1 and another image of Mars. So that is it for our survey of the space program, the early space program. Join me in Lecture 6 when we talk about early human spaceflight, the first humans to go into space.